so over finite field GP. And at first, so I want to explain so where I come from. So Kyushu University is so located so near near Korea. So here is Fukuoka. This is the city so where Kyushu University is located, and it's near than so Kyoto or Tokyo. Just 1.5 so hour flight. I could come to Busan at first by ship, then I can take KTX. It's earlier than to take flight 1.5 plus 3 hours by bus. Okay, and Kyushu University is located Fukuoka. It's a Chinese character, and founded just 100 years ago, and one of the 7 top universities in Japan. And we have many foreign students, 66%, and we have an English course. And if you are interested in come here, we are very welcome. So after graduating to your PhD, we have some postdoc position, we are also welcome to come to our university. Okay, so let's start the scientific talk. The problem I deal with in this talk is the discrete logarithm problem over finite field GP. This is a prime number, and in this talk I explain mainly extension degree 1. Namely this finite field is called a prime field, and this prime field has been used in many cryptographic applications. For example, DSA, this is a standard called digital signature algorithm in the United States. Or this problem has been used the Heuristics key exchange problem. For example, SSH, it is a famous protocol, which you can log in to the remote server. You can securely send your password to the server. And in the SSH, there is a implementation of the Heuristics key exchange. Or probably you know, SSL. Also have an option to use DSA, and they implement these into internet these cryptographic protocol over this finite field GP. Therefore, it is quite important to see the security of this scheme by analyzing the discrete logarithm problem over finite field P. Okay, what is the discrete logarithm problem? I define here. We choose a prime, usually 1024 or larger, 2048 bits. And we encode the finite field GP to this star, like this in this talk. Well, many implementations use this representation. From 1 to p minus 1. And what's the order of this group? GFP to the star is equal to p minus 1. And we deal with the multiplicative group of the finite field, GFP. And it is known that this multiplicative group is a cyclic group, and it is easy to find a generator. Then we set it at G. Usually we generate from G equal to and check it is a generator or not, and if it's not generator, we choose G equal to 3, and then we can quickly find generator G in practice. In theory, it is quite difficult problem to prove. There is such a small generator. You need extended Riemann hypothesis. So practice, so it's easy to find. So for 1,000 or 2,000 bit P. And so then we choose target element A from the finite field, so GFP. And so what is the discrete logarithm problem? So it is it is a problem to solve G and X which satisfies this equation, G to the X equal to A. So namely, so we compute G to the power of X, then so if it is equal to A, then so we want to find such a X which satisfies this equation. And because this is a generator of this multiplicative group, there is a unique such a G, such a X in this range from 1 to P minus 1. Okay, so we denote so by log GGA, so the discrete logarithm of A to the base G. Okay. So namely, this problem is for input prime P and generator Z of the multiplicative group and target element A. So you try to find the discrete logarithm, so log GGA. Okay. So then, so how can we solve such a problem? The most simplest, straightforward algorithm is so an exhaustive search. Namely, for x equal 1, 2, 3, and so on, we check G to the X equal to A or not. Okay? Just we compute G to the 1, then we check it is equal to A or not. If not, then we go to the next candidate 2, then we check G to the, so the G squared is equal to A, and so on. And so from 1 to P minus 1, so we definitely have the solution X, which equal to so A. Then, so we can find the discrete logarithm. However, because it requires so exponential time, or P. So it's too slow. And so we want to know how can we do better with some trick. So there are some algorithms. So when we specify P equal to so P minus 1 is divisible by only small integers, then we can do so something better. So most general trick which improves the efficiency solving this problem is Pollard law method. This is very clever idea, and so this method uses the Basel paradox. So using this Basel paradox, we can reduce the exponential time quite a lot, so square root time, so P to the 1/2. Still, this is exponential time, but we can reduce the time quite a lot. Later, I explain this algorithm. In the beginning of this talk, I overview some known techniques to solve real problem, and then later I explain the new result. Okay. And so for general group G, currently this is the fastest algorithm to solve the discrete logarithm problem over the group. However, if we see the problem, so in particularly over the finite field GFP, we can go lower than this bound. And so how can we go lower? The idea is to use a small number, because we can represent integer by product of small prime numbers. It means we can represent the discrete logarithm problem using very limited small numbers of primes. Then we can embed the discrete logarithm problem to the linear algebra problem. And this technique is called the index calculus method. And so when we prepare sub-exponential size of matrix, namely sub-exponential size of small prime numbers, then it is in the case this technique is most efficient, optimal to carry out the index calculus method. And so this running time is estimated this one. E to the this number, and see the constant, the small o tends to 0 for enough large p. And so this part is very tricky written. This comes from the mathematical property of smooth numbers. So when we analyze how many numbers are smooth, then we get this formula. So this is because of the combinatorics property of smooth numbers. And so here you can see log p squared. Here's log p squared. So therefore this is between exponential time and polynomial time. Log p to the n. The between. Therefore we call it sub-exponential time in this case. For large p, for example, more than 100 or 200 bits, this is much faster than square root time. For small p, for example, 1,000, just 1,000 or 1 million, it's of course faster paradox is faster. But cryptographic purposes, we can estimate this sub-exponential time to do a secure parameters. And the question was, can we go further, much lower than this bound? The index calculus method uses smooth number, and when you use just integers or some elementary mathematics, it is quite hard to break this lower bound. However, there was a breakthrough in 90s. Number field NFS has been found. This is currently asymptotically fastest algorithm to break the discrete logarithm problem. And interesting point is this number field sieve was first developed for factoring purposes, namely to factor composite number into prime numbers. And as you know, factoring is underpin the security of RSA crypt system. And I will explain later. This number field can be relatively easily adapted to the discrete logarithm problem case. And interesting point is that in the both case of factoring and real p, we have the same speed. For enough large p, namely this is the speed of the number field C. The difference from the the standard index calculus method is exponent here are different. So the previous one, so is 1/2. But here we have 1/3. And here become large, 2/3 from 1/2. But so here is log p term. Therefore here is the dominant part, log p 1/3. And so this exponent makes the speed of solving DLP much faster. So especially for large numbers. And so in this talk, I want to deal with NFS in the second part of this talk. Okay, at first I want to explain this two methods, Pollard law method and index calculus method. Maybe you are already have studied this algorithms. So just for warming up, so I want to explain this two methods in next 30 minutes. Okay. So let's start with Pollard law method. So Pollard law method uses a random map F from GFP to GFP. And so from Birthday paradox, we can find a collision for iterating many efforts to the initial point beta. And ij are different, and so this we call it collision. So with high probability after iteration of p to p squared. Of the random map F. And so this Birthday paradox tells us chance is high enough to find such a collision after these iterations. Okay, then we want to construct such a random walk on finite field. And how can we do it? So if we want to construct such a random map, there are some methods. But if we construct very random map, but it could be not enough efficient. And so if we construct some simple random map, maybe it is not enough random. So there is a trade-off, and so Pollard, in his paper, he suggested that we use pseudo-random map. In the following, like this. How can we construct such a pseudo-random map? And this map is quite an efficient map. So we divide the finite field into three parts: G1, G2, G3, and their cardinality are almost same. And they are disjoint. So we say GP equal to G1, G2, G3. So disjoint union of three subsets. Then let's compute like this. So we are dealing with a group. Therefore, group has a one operation, multiplicative operation. And if beta is G1, we just multiply the base point G. And beta is in G2, we compute squared, beta squared. And beta is in G3, we multiply by the target element A. So as you see here, we have only one multiplication. It's a minimum to do this operation. Of course, there are some improvement. In some case, we drop here multiplication or something. So here seems very efficient. And so, so applying this pseudo-random map, so we perform the, we iterate this map many times. Okay. Okay. Then we accumulate the exponent, so which will be changing by the action of the random map F. So at first we generate random x0 from this set, and so we say beta 0 equal to g to the x, and so we set y0 equal to 0. Then so we define beta I is equal to f of beta I. Beta I plus 1 is equal to f of beta 1. And so, as you saw in the last slide, we just multiply either base G or target element A. Therefore, we can represent beta I with this form, G to the xi, and so A to the yi. And so we want to keep this exponent, and so we want to use it to solve DL problem. And then, what's the relationship between xi plus 1 and xi, and yi plus 1 and yi? This written like this. Because we just multiply in the case of G1, G, therefore the exponent of G becomes plus 1, and here n is the order of group, in this case p minus 1. And in the case of y, here, we don't change yi here. And in the case of G2, we compute squared. It means we compute 2xi, 2yi for both sides. And in the case of beta in G3, we don't change here, and here is yi plus 1. Very simple way. Okay, therefore, we can track the exponent by checking the index. Okay, with the initial value x0 and y0. Then once we find a collision, then there is a integer I and k which satisfies this one. It means once we find the collision, then there is a loop of collision again after applying k times this one. So this is of course after finding collision this happens. It means we have this relationship. So substituting the previous relationship, we have this one. Namely, we can solve DL problem because A equal to D to the X, then we have this relationship. So modulo P minus 1, then we can find the target, discrete logarithm X. Okay? In some case, we cannot solve this equation because greatest common divisor is P minus 1 and this coefficient of X are not 1, but usually it is a very small number, therefore we can find unsolved portion of X by exhaustive search. It is enough first. Okay, then we found X. So in the real implementation, how can we realize this attack? So it is explained in the next slide. Okay, like this. Input is finite field GFP, and it's generator D, and the target element A, and we also define random map. The goal is to find the x which satisfies g to the x equal to m modulo p. And so we prepare this disjoint sets. And so we start with x0 and y0 and beta 0. And the point is, so we prepare omega here. This is called a distinguished point, which was initialized with a. And so we change distinguished point in the algorithm. And so which try to find the collision. We don't save all points, but we only save distinguished point. It is a point. So then we can save out of memory. We don't have to save all points, just distinguished point. In this case, I use just one distinguished point. So some improvement use more distinguished points. Then beta I is not equal to distinguished point. We perform the iterations. And so here is updating the point by random map. This is random walk point, and we change I plus 1. Okay, increment here I, and so point is here. So we check only the point. So 2 to the k. K start with 0. And so it is 1 start, but next is 2, next is 4, next is 8, and 16, and so on. Therefore, we keep only the distinct point with the length, so with the exponential size of 2 to the k. So first is very narrow, but so it's rapidly increasing. Then we have enough chance to find collision in this case. Then finally we get collision with distinct point and beta I. Then we finish the loop. Then we found the this relation, namely we found the DL. So the discrete localizing x. Okay, and so this is a very basic scheme. So proposed by Pollard, and so after that, there are many improvements on this scheme. So for example, if we apply elliptic curve case, elliptic curve case, we have some special efficient map like Frobenius map or other maps. Squaring is more efficient than multiplication. Then we can improve this part. So this random map. Well, as I said, we can prepare more distinguished points. For example, 6 points. Then we change this loop instead of just 2 to the k. We change some more branches. Then it's become much faster. However, whole variations of this Pollard law method has same asymptotic speeds, namely p squared. Square root algorithm. Difference is to reduce the constant term of the speed. The constant term is still out of influence to decide the security parameters. Therefore, it is very important research topic in cryptography. Okay. Let's go next. Okay, let's move to index calculus method. When you look at textbook of cryptography, you sometimes see this algorithm. But this algorithm has very long history. When I see references, some paper sets, the basic idea has been developed 1920s, almost 100 years ago. Some mathematician try to find this prototype of index calculus method, and the motivation to solve this index calculus to develop this index calculus method it was pure mathematical interest in the beginning. But after the invention of RSA crypt system or discrete logarithm based crypt system, so we switched to the application. So the application of these cryptographic protocols are secure or not. Then so when I checked all the references after 80s, especially after 90s, there are many research survey papers in this area. And so in this slide, I want to say very basic idea why index calculus method can go lower the square root barrier. And so the main idea is we prepare factor base fp. It is a set of prime numbers smaller than b. Namely, for example, b equal 100. Then factor base fp contains 2, 3, 5, 7, 11, and so on, up to 100. Then we call our integer lambda is a b smooth when lambda is has a prime decomposition of primes q smaller than fp, contained in fp factor base smaller than bound b. Okay, so we don't care the exponent here. Sometimes exponent is quite huge. But if you randomly choose integer lambda, exponent is not large in general case. But for small number, 2, 3, 5, 7, maybe exponent is, for example, 20 or 30. So for a given 1,000-bit integers. So important is the size of this prime number q is smaller than b. And this is now purely mathematical question. So what is the probability for given lambda smaller than x? So can you estimate the probability lambda is b smooth? B smooth. It means for given x and b, can you estimate the probability of smoothness? And there are many papers on that topic. And here's one result. And I want to use this result for estimating the efficiency of index calculus method later. So here, let LPC is equal to this one. So e to the c plus 1, this one. This one is already shown in the previous slide. So in the case of index calculus method, so this is sub-exponential size for given p. Okay, let's say an integer lambda is an LPC smooth integer. Then the probability this lambda is LPC smooth is this one. This is very low in general. But we can estimate here -1 over 2c, and you substitute here. So it is a relatively small number. So intuition, this estimation is for example, you have 100 bit, then you can estimate 50 bit smooth or the 25 bit smooth, and so if it is 50 bit smooth, then it's relatively high probability. For example, 40% or 50%. But if you have just 10 bits smooth, then it's a very low probability. It's sub-exponentially, so decreasing the probability in the bit length of P. So for given 100 bits of prime number, so you want to find 10 bits smooth, then so it is so maybe 0.000000001. But there are some probability, but very small. Okay. Then so this is also well known in mathematics. So as a prime number theorem. So conjectured by Gauss and proven by other mathematicians. So the number of factor base is equal is written so pi b, and so this has this so size b over log b. It means if we have enough prime number, so it means randomly chosen so b, so the prime as an integer smaller than b, we have so probability. So the number is p is just 1 over log b. It's very high probability. Then so the expecting so running time so to generate so b relationship is so we want to generate so many smooth numbers, and so we want to so accumulate many relations. Let's say we want to accumulate this LPC so relations. Then so we need so this time. Here is the probability of B smooth, and so here is the number of the we substitute B here, and so we divide it by probability. This is a heuristic so estimation, but we get so this one. So in order to generate many so iterations for a given bound B LPC, we expect it takes so this sub-exponential time. Here, this time is depending on the so C, constant term C. It is therefore very important to optimize this constant later. Okay. Then how can we embed this relation to the so linear algebra? So it is explained in this slide. So what we'll do is so instead of solving so x so itself, we try to solve the discrete logarithm for small prime numbers. Namely, so we want to find the xq for target q. Here is instead of a, so we want to solve this q. Then we denote xq as a discrete logarithm of this equation. And so here, how can we solve this one? Idea is as follows. We generate so random. This is z. It's a mistake. So here z. We generate random z, integer z. Then so we know the probability how so the probability of so becoming this number is a smooth number. Then so we can so compute prime decomposition of g to the z here like this. Sometimes we have a prime factor larger than b, then so we throw it away. We don't keep it. So randomly we generate z, then we compute prime decomposition, then the maximum prime factor is smaller than b, we keep it. Otherwise, we throw it away. And we know the probability in the proof so successing of so to get so two smooth number is in the previous slide. So once so we have this so prime decomposition of B smooth number. Then, so we substitute here, G to the XQ here. Then, so we have same base here, G. And so the number of summation is the number of factor base. Then, so we extract only the exponent part. Then, so we have this relation, modulo P minus 1, this relation. It becomes summation here. And so, as I said, so Z is chosen by ourselves, and the exponent is a prime decomposition. Therefore, we know Z and so EQ. What we want to know is the exponent here, XQ, which is exactly the real problem of target Q. And so we have so many relations. Then we put in the row each relation here. And so if we gather relations more than the cardinality of FB, then we have we can solve this linear algebra, XQ and ZJ, modulo P minus 1. Okay? As I said before, so number of primes smaller than B can be estimated by prime number theory. Then we can know the size of matrix here. It is as large as B over log B. And so here we have trade-off. If we have many relations, then we make B large. Then we have many factor base, and so we have to gather many equations. In that case, linear algebra becomes very large. Very large. And so it becomes slow here. And if we make B small, then linear algebra becomes small, then we can solve faster. However, if B is small, the probability to find B smooth number becomes low. Therefore, we found optimal B. Pardon me? This size of matrix?
Yes. You have matrix equation there.
Yes.
And what's the, you just want to find XQ or EQ?
XQ. EQ is known. It is an exponent of prime decomposition. You compute G to the X, and you compute the prime decomposition here. Therefore, you know this EQ. What you want to solve is this. No.
EQ is already known.
Yeah, yes. EQ is known, that J is known. What we want to solve is here, XQ. Just standard solution of linear algebra. Okay? Okay. So we know that there are many ways of solving this linear algebra. And so this linear algebra is very sparse. Namely, we have many zeros. Almost entries of the matrix are zero. And so in that case, we can solve B squared. Pi b is the number of the factor base, and so the order of solving the linear algebra is just squared here. And it is equal to LP2C for choosing this B. Okay? And so therefore, comparing equation 1 and equation 2, So this choice is already optimal. So for index calculus method, and we get this theorem. So this theorem try to optimize the constant term c. So from 1 to the total running time of the index calculus method is LP max, so c plus 1 over 2c, and 2c. Then we make c equal to this number. Then so it is a minimum, optimal point. Then we can estimate this asymptotic complexity. And so there are some researches which try to reduce this part of C much smaller. So using some lattice technique or other idea. Okay, here. After finding DL for small prime numbers, so how can we solve the target? So A. So it is done like this. We just multiplying with g to the y. Y is randomly chosen integer. Then we can expect also this can be factorized with a smooth number. Then we already know the DL of Q. Therefore, and so of course we know Y. Therefore, the discrete logarithm can be solved.
How do you find EQ to some extent?
Pardon me?
How do you find EQ?
EQ is for example, g to the x is 15. 15 means 3 times 5. It means exponent 3 is 1, exponent of 5 is 1. Other exponent is 0, 0, 0, 0, 0, everything 0.
You vectorize over integers.
Over integers, yes, over integers.
Then it's a sort of small price.
Yes, only small price. You compute for g to the x modulo p, yeah? Then, for example, it is
Then you factor.
just factor, yeah. And so how can we factor it? So because we know factor base, for example, 2, 3, 5, and 97, and we can divide just
Usually the size of FP
it is big, but it is upper bounded by sub-exponential. And so what we want to do is we want to solve in the speed of sub-exponential. Then it is not exponentially large. It is upper bounded by sub-exponential size. And so B is, for example, much smaller. What we want to solve is very huge. P. But B is very small comparing to the target. Finite field.
So in practice, you find EQ without any special technique?
So yes, we can find EQ by exhaustive search. Exhaustive search, yeah. Dividing by 2, dividing by 3, dividing by 5. Then now it is because B is enough small, then we can do it.
Not all the first time of the kind of thing, right? There are some specialties, should be some specialties.
Yes. In some case, it is not be smooth. Then if we compute all factor base divided by 2, divided by 3, and divided 97, then still some larger prime number, we throw it away. We don't keep it. No. If we want to find perfect factorization for any z, it is impossible. We just try. We just divide only the factor base. It's a small portion. then we have additionally more prime number, then we ignore it. We just compute only small portion of primes. And so then it is upper bounded sub-exponential then. Okay? Okay, now and the individual logarithm is also same. Okay, let's go to the next topic. So what you saw in the index calculus method is to use B-smooth number. And so if we use only B-smooth number of integers, we cannot go lower the bound of sub-exponential of the order log p squared. The idea we can break the lower barrier is to use number field or function field. And in this slide, I want to explain the known result of number field sieve and function field sieve for any finite field of characteristic p, any p, and any extension degree. P could be, in some case, just 2 to the n, while p could be very large and n equal to 1. So we deal with all possible finite fields here. Then, we know that, we can solve dlp over any finite field by this speed. So all algorithm has this asymptotic speed. So 1/3 here point and for some constant c. And so here, q, instead of p, we have q here, p to the n. Okay, the first one, prototype of number field sieve was proposed by Kopasnis. So he introduced to use function field sieve. So in this paper, stock 84, and his algorithm is effective only for small characteristic. To use ideal decomposition in the function field. And so Gordon adapted the idea of number field sieve of integers to the DL problem case. This is a simple adaptation of number field sieve of integer to DL problem. 92. After that, Adelman extended the idea of Kopasnis, and he developed so-called function field sieve. 94. And then there were two important improvements in practice. So there are some problems. So in the number field sieve proposed by Gordon, it's very difficult to separate sieving phase and the linear algebra phase. And this paper successfully solves the problem. We can divide linear algebra part. So by introducing so-called virtual logarithm. And this function field sieve improvement are also some very clever idea. We can generate polynomial for function field sieve very flexible way. Okay, then Eurocrypt 2006 and Crypt 2006 two papers try to solve some special cases. And the interesting point is number field sieve is very effective for large characteristic. And function field sieve is very efficient for very small characteristic, but large extension. And if we deal with the medium size of so characteristic or exponent, then we could not achieve this asymptotic so speeds. And these two papers has a very similar idea, and so they improve function field sieve case, so relatively large prime so characteristic. And in the case of so this paper, so they improve number field sieve for relatively large extension DB. And using the two results, we now know so all algorithms, any combination of P and N have this asymptotic so speed. It is just so 5 years ago, so we achieved so this speed for all possible finite fields. Okay, and so so this is a theoretical result. So, and the point is, so now, so we want to use so real problem-based crypto system in your life. Then we have to decide the bit size of P or N. Then so we have to say, for example, 1000 bit or 2048 bit, and so we should propose that so this bit size is currently secure, and so it is expected secure for next 3 years, 5 years. But so maybe 1024 bit is not anymore secure. Then we should switch to 2048 bit, and we can use it for next several years, blah blah blah. And so in order to estimate so secure bit size, we need experiment. So we have to see the current technology of computers or hardware development. Or so, for example, recently we have so very efficient GPU, graphic card, GPU. So unfortunately, the talk is cancelled tomorrow. But so there are so many results. For example, Chen, so he implemented so cryptography on graphic card, and it seems very faster than CPU. In that case, we have to estimate implication of GPU against these algorithms. Or nowadays we have cloud computing, and so it seems so cheaper than to buy so many PCs or to buy our own servers. And so we want to know that so maybe cloud computing can so accelerate the practical speed of this so number field sieve or function field sieve. So in order to estimate such a so secure key size, so many so large scale so experiment has been done. And as far as I know, the first so large scale so experiment was done here, 91, and so they solved about so 200 bit so real problem over finite field. Interestingly, this real problem, this size of the prime number has been used the file system of some server, and so I guess this is first so practical crypto analysis of DL-based crypto system. So nowadays, I won't say we can solve these 200 bits just a few minutes, not too difficult kind of technology. But so in those days, it was the first breakthrough for P. Then there are so several ways, and they implemented so index calculus method, not number field sieve here. And the first number field implementation has been done here, 98. This was so implemented by Denny and so Weber in those days in Germany. And so this is more than 400 bits. And so this problem is quite famous as a Macaulay challenge. So Makari is the former president of ISTL, and he said, so okay, let's set some challenge in his paper, and he said, so if someone who solve this challenge, then he give the solver $100, and so they received $100 in Crypt 98, and they presented the paper Crypt 98, so this report of breaking 420 bit or so.